Hello, good afternoon, everybody. Hope you are doing all right and hope you're having a good time. Um, Yesterday we had some issues with the internet. So today I am actually using um, a technology called, multi sections. Okay, so this technology hopefully is going to provide us the highest reliability and we won't face any problem going on. So again, my apologies for the disturbance that happened today. It won't happen again, and we can um, basically continue of what we are saying. So what I am doing, I am actually um, um, basically providing uh, I am also I am actually doing it in multi different ways. First of all, I do have access to two computers. Also, in order that to make sure that we have a complete reliability, I am making a video of this conversation and I put this video also on the system. So worst case scenario, I can call your teacher over there in China, and then you can watch the video that is basically video of this lecture, video of the same conversation. So hopefully we won't have any problem today and also going forward with internet or any other problem. Anyway, if there is any problem, always let me know, and if there is any sort of technical difficulties, I would be happy to resolve that as soon as possible. Anyway, today the conversation that we have, the agenda that we have is about the first of all, we having a revision over data logging. As you know, today is Tuesday, and Tuesdays we look at data logging and signal conditioning. That's the data acquisition and signal conditioning is basically the main topic of the day. So first of all, we're going to have a revision. After the revision, we talk about the data logging questions and practice them. Then we continue the lecture on data logging. And then after that, I would present the first assignment that you need to do for this course. Okay, we have a tab actually for assignments. So we'll discuss that as of today. So now, to go back to the data logging, first of all, I wanted to show you, revise you the stuff that we did, and then after that, we're going to do multiple questions. So if you look at this tab, what we realize that the system, the data that we have usually are actually analog. The data that comes to the system, the physical network that we have is analog, and what we can do, we can break it down to smaller parts. Okay, and we do the sampling means that taking some samples of the data, and by doing that we can feed that to the network and feed that to the PLC and other controllers that we have, and then the PLC would be able to see it. Otherwise, this data is going to be continuous and is happening all the time. So it's important to do the sampling and introduce a sampling frequency. We said there are different ranges of data that are actually a standard. So 0 to 5 volt, 0 to 10 volt, minus 5 to 5 volt, and minus 10 to 10 volt. There are some standard ranges that we have. We have obviously other ranges too, but we wanted to basically start and work on these ranges first. The number of bits of and then we said as well, we have an 80D converter and the A to D converter is also going to change the samples. Once the sample taken, going to change the samples to digit, to numbers, and then store these numbers into the memory, into basically a binary memory, as you already know. So the signal that we have like that is gonna be taken sample of that, so sample, and then gonna be converted. And we realize that the samples definitely got to be good numbers of samples, okay? And we need to make sure that we have enough samples. If we don't have enough samples, like for example, if we take a sample, one sample from here to here, what's gonna happen? We are going to miss all the way for this signal that what's happening from here to here. So it's important that we actually look at that carefully. Then we looked at some of the numbers that we have about the digitization, and we realized the word resolution, okay? We understand the resolution is related to number of bits that we have. So 2 power n, well, n is number of bits, is giving me the resolution, and resolution is gonna be R maximum minus R minimum, which R minimum is the minimum resolution, R maximum is obviously the maximum resolution that is taken. Then we said, well, this digitization is going to definitely cause some errors, okay? And this error is not because of the sensitivity of the system, it's because of the digitization, because of the number of bits that you can store there. And if you wanted to work out that how much is this error, V error, the voltage error that we have, gonna be use this formula for that, V maximum minus V minimum over 2R, okay? And then we said, well, I call that D instead of V1, but if you like, you can still make use of V1. So the digits that we have, the digit that assigned to any voltage when the input voltage gets in, gonna be Vn minus V minimum over V maximum minus V minimum, okay, times R minus 1 plus R min. And then we have an integer. That means that we just look at the integer number that we're finding, and then we said if we have that the integer number, if we have a digit, then we can put the digit here, minus R min over R1 minus R1, R minus 1 times V max minus V min plus V min. So it's the formula that actually helps me to work out that for any digit, how much is going to be the assigned value for that. Okay, so obviously we looked at multiple scenarios, like for example 10 bits, to see what is happening. So like for 10 bit, we realize that if our range is from 0 to minus 10, so yeah, if our range is between 10 to minus 10, okay, plus and minus, so actually our accuracy came out as plus and minus 9.8 millivolt, as you can see that here. So we had examples like that for different minimum and maximum, that how much is the value, and we basically worked that out right here. So basically that was a revision that we had. The other thing that was an important one was about taking a frequency, okay? And we said we don't talk about the frequency errors, but instead we talk about something that is acceptable or not acceptable. We realize that if we're not taking a correct frequency, what's gonna happen? Then the samplings won't estimate when won't properly estimate the signal. Like here we have a sine wave. Okay, the sine wave now you can see that estimated to something that definitely is not similar in any way to the sine wave. In fact, it is having a different frequency. It is again something like a sine wave, but in no way it is demonstrating the sine wave that we have up there. And we said we have a formula for frequency, and we just say that the frequency of A to D got to be more than, okay, the frequency of A to D got to be more than 2 times of the frequency of the signal. That's the minimum frequency required so that we get in a correct information. If we go less than that, so the frequency that we get in is wrong. So frequency of I to D is a sampling frequency, and frequency of the signal is maximum frequency of the input as we have. So you may actually have multiple frequencies, but you need to go for the maximum frequency, and you need to make sure that your frequency is at least more than twice the frequency that we have. Well, we pretty much stopped here last time, and we solved some other things, even though we know that there are noises and other stuff around, but we will looking at this part a little bit after that. Then of course we looked at A to D questions, okay, and some examples that, as you can see, some stuff that I provided for you here, okay, and some examples that we actually looked at that, and we analyzed that, and we practiced them. So hopefully that it was making sense to you. Okay, so now let me actually again to have a couple of formula. Today I've wanted to explain this a little bit in a different way before we move on to more advanced stuff. Okay, so as I said, this formula that we have are very important. So again, I copy them, okay, and I keep them for the next question. Okay, another example. In the test, in the exam, you're gonna have this formula, so you don't really need to remember them. As long as you are able to use them, you should be fine. Okay, so it's a question that I have here. I demonstrate this question in a different way slightly, and then after that we're gonna have so what is this example? Example 3. Okay, example 4. Okay, you have an 8-bit, okay, an 8-bit A to D. The input range is from 0 to 100 volt. Okay, now so we have the input range that is given to us from 0 to 100 volt. Okay, determine the output digits. Okay, determine the output digit means that the digit that actually your ATD gets for, okay, 20 volt. So what's happening, the explanation of that, if I wanted to explain that, well, basically we have the A to D, And the A to D that we have, here is the A to D, analog to digital converter. The analog to digital converter that we have, the input for that is, okay, the input for that, what is the input for that? The input for that obviously is an analog signal. Okay, the input for that in this case is 20 volts. Okay, what you're getting here outside is a digit. Okay, so we wanted to know that what is the output. Okay, I do it like that so that we actually get more idea as what is this digits. Okay, 20 volt gets in. How much digits is actually I am going to read. Okay, so what I do again for this question, I go and I looked at my formula that I have. Again, I have the resolution. Okay, resolution equals this much. Okay, so that is going to be 2 power, because I said 8, so n is 8, so it's going to be 256. Okay, now V error, I didn't ask for V error, so see, I can be actually selective here. Okay, so I didn't ask for V error. I don't want the error in this question. Instead, I need the digits. Okay, so how much is the digit? So the digit going to be, the integer, okay, of Vn. How much is Vn? Well, Vn in this case, as you realize, is 20 volt. 20 volt was the input voltage, so it's 20. How much is V minimum? The minimum voltage that we said was 0, so minus 0. How much is V maximum? 100 volt. And how much is V minimum? Well, 0. And times R minus 1. And how much is R? Well, we said 256 upstairs. Minus 1 plus R minimum. And R minimum, we put 0 in most cases here. We actually don't need this one here, okay, as well. Okay, so now I just do the calculation but on the background, so 20 divided by 100, okay, so that's times 256 times that is going to be 51.2. okay, so how much is integer of 51.2? so 0.2 is going away, so it's gonna be 51. Yes, that's the answer, guys. So the output that we have is 51 exactly. So basically the PLC is giving us 51 here. Now another question, okay, so you said 20, okay, another one. How about when the input become for example 60 volts? Okay, how about when the input becomes 60 volt? Well, if the input becomes 60 volt, all we need to do is to just change this number and see what we're gonna get. Okay, so I just copy and paste this, so you can see that our VN now is 60 volt. Okay, so let me use a different color for that so you can see that. So instead of 20 I have 60. So 60 minus 0, okay, 255 here, and then it's gonna be how much? Let me see what is the integer that we're getting. So it's going to be this time is going to be 153.6. So integer of 153.6. Okay, now it is going to be rounded up because it is 0.6, so it's going to be 154. That's the number that your PLC is getting. Okay, another one. Okay, let's have on the same topic, let's change this question and see what we're gonna do right here. Okay, example 5. This time you have an 8-bit, okay, you have an 8-bit input range. Again, let's keep the 8-bit, but the range, the input range is from, now I'm changing the input range from -10 volt to 10 volt. Okay, determine the output for the digits. Okay, I go for 3 volt. So I wanted to see that if I got 3 volt, how much I am getting on my microcontroller or my PLC or whatever it is. Okay, it is very, very important. Why? Because the digit is the one that I am having, not actually 5 volt, because this -10 not actually 3 volt, because actually the -10 volt and then 10 volt, they all, this range gonna be converted to numbers, and the numbers are the one that I am going to have all the way through. So let's see what we can get. So in this case, -10 volt to 10 volt. Okay, hopefully you see that properly. Yeah, let me see what is the font. 16, I might make it like 18. Okay, now again I need which formula? I need the formula that I have right here. So let me copy and paste this formula. Look at this. Each time I look at the formula that I have, and then I can play with the formula. Okay, again I cut and paste the formula. It's 8-bit again, so what's happening are going to be equal to 2 power 8, which is 256. Okay, it's possibly a little bit smaller. Okay, 256. Now I have this. The next line I have the formula to copy in, and actually the question is about the digit, nothing else. Even the error wasn't asked for error, because last time we practiced the error. Now question is that how much is actually the digit that I am having. Okay, so then Vn is 3 volt. Okay, so 3 volt, I change it with 3. Vmin, minimum voltage that is possible, is -10 volt, -10, and underneath V maximum is 10 volt, positive 10 volt, and V minimum again is minus 10 volts. Then R, as you can see, is 256 again. And R minimum is 0. So again, I do the calculation to work out that how much is the value for that. So I have 3 minus 10, which is gonna be 13, and over 10 minus 10, which is going to be 20, okay, and that is going to be times 256 minus 1, which is 255. The answer gonna be 16.75. okay, however I need the integer for that, so integer for this value, oh dear, integer for this value, well, it's going to be one number higher because it's integer, so 166. okay, so I found the answer. So that means here for this range, if I have 3 volt, I am getting 166. okay, let's have one more example. okay, how about minus 2 volt? How about, okay, the digit for minus 2 volt? Yes, well, it is again going to be very similar, so the resolution stays the same, but all we have to do is to just enter the minus 2 volt as required. So what I do, well, the Vn was 3 volt, now it's gonna be minus 2 volt. Well, minus 2 volt minus 8 volt, sorry, minus 2 volt minus 10 volt, which is gonna be, well, 8 volt, 8 by 20, 8 by 20 times 5, now times 255, so it is 8 by 20, it's gonna be 102. Integer of 102, and we know that integer of 102 again is 102, okay, as we have that here. Now what is it gonna happen if we wanted to go for, well, okay, for a different number? Okay, for example, what is it gonna happen if we look at, for example, again one more example to make sure that you are having it. I hope that you are doing this stuff as I am doing it. So how about, well, I just go for a different number. How about minus 10 volt? Minus 10 volt was the minimum value, right? Isn't it? So let's try that and see what's gonna happen for minus 10 volt. Again, I copy and paste these things, the digit, as you can see. Okay, digit equals integer of, okay, now here is minus 10, okay, minus 10 minus 10, which is plus 10, gonna make it 0, okay, and 0 over any number multiply by this number gonna be obviously 0, so 0. Yes, that's right, that's the digit that we're getting. And it's very important to understand that the minimum always and often returns 0 for the calculation that we have. Okay, Now, this is the things that we did. Now I wanted to turn the question in a different way and ask it in a different way to see that how it works. So example 6. Example 6. Okay, you have an 8-bit A to D, okay, A to D converter, obviously. The input range is from minus 10 volt to different 10 volt. Okay, now I don't say determine the output digit for 3 volt. Okay, well, I say determine the real value. Okay, determine the input value for, okay, I wanted to know that determine the input value for digits. Okay, let's just let's write it like that. When the microcontroller or PLC is showing, okay, showing what? For example, 127. So we have 127. Okay. Now, question, how much is this 127? How many volt is this 127? Now, again, we can look at the formula that we have, all of them, and see that which one is actually useful to us. So let me actually copy this here and show you that the case that is actually different. Okay, here we have the A to D. We don't know how much is this voltage, but we do have the digits. So that's the case that we have. So again, I go and copy and paste the formula that we have. Okay, well, this is the formula I need. I need VC when I have the digit. So I come here, I need VC, I need the V calculated, the voltage that I have, voltage that is actually the input voltage when I have the D here. Okay, so how much is the digit? I can see the digit is 127. That's a number that is showing up. Okay, well, obviously I need to first work out the R and R minimum. So again, let me do that. So make sure that nothing is left, because I am of course relying to the previous question, but let's make this clear. R equals 2 power, well, it is 8-bit again, so it is making 256. And again, if it is not mentioned anything, then R minimum R min is 0. Okay, and then R max is going to be the maximum that we can. Well, we don't need R max, we have R. Okay, here. Now D, well, how much is D? Let's keep this formula so that you can go back to this note. Well, how much is D in this question? As we can see, D is 127. 127. How much is R minimum? Well, in this question, as we can see, R minimum is 0, because it's not mentioned anything. And R is how much? Is 256 minus 1, and then V max minus V min, as you can see, is about 10 volt for V max, and V min equals minus 10 volt. Okay, And how much is V mean? V mean again equals minus, so I actually get rid of that, minus 10 volts. So let me see how much is the answer. So 127 by 255, 127 by 255, that is multiplied by 10 minus 10, which is making it 20, and then plus minus 10. Well, the answer is minus 0.3922. I just sort of wanted this much accuracy. Obviously I can go further as required, but well, anyway, I just look at 4 significant numbers for this question. So you can see that basically this is the number that I am getting, and as obviously calculated. So basically the number 127 is not really 127. So what is it? It is in fact 127 is what we're getting, but the real value that we have is minus 0.3922 that we're getting as 127. Now another example, let's just have another example. Okay, how about the input voltage for the input voltage when the reading, the microcontroller or PLC reading is 221. Okay, so I wanted to see that what's gonna happen if I have 221 and how much is going to be the value. Okay, so again, what's happening, I make use of this formula. In fact, I can use this formula. Why is it? Because everything is the same. What is different? Only the value here is different. So 221 that I mentioned, I put that here, and I go for 127 minus 0. Okay, I change this 120, which is the input digit, to 221 this time. Okay, and then 256 minus 1, 10 minus that, minus 10, which is everything is according to the calculation, but only my number is different. And now I replace that number with 221 in my calculator, and I work that out, and I am getting, this time I am getting 7.333. Again, go for 3 significant figures. So you can see that you can actually work that out, and if the digit is given to us, we are able to identify the value accordingly. Again, I am hoping that you do this with me. Okay. Oh, well, actually you said example, so let me call that section B. Now, sections, another example. Well, let's just change the example to this time. We change the bits as well, and then see how things gonna change. Okay. Now, example 7. Okay, 8 bits. We had 8 bits. Now I go for 12 bits. 12 bits A to D. 12 bits A to D. The input range is from minus 10 volt to 10 volt. So you can see that the input volt range here and everything is the same, but what is going to be different, the only thing that we have changed is the accuracy of the PLC. Obviously the number of digits is going to be different to determine the input value when the, oh my gosh, I said microcontroller, this is actually microcontroller, when the micro, okay, so going back to that, is this crazy micro change to micro controller showing 127. So what should I do here for this question 7? I need to first work out that how much is my resolution, okay, because my resolution gonna be different. So what's happening are going to be equal to, are going to be equal to 10 to power 12 in this case. Well, I don't know the answer, so let me just go and see what is the answer. 2 power 12 is 4096. 4096. Okay, so that's the resolution. Again, nothing is mentioned about the minimum resolution, so I suppose R minimum equals 0. That's usually happening, that we consider that, okay, we start from 0, unless obviously it's stated the other way. Okay, now the type, now we wanted to look at VC. Okay, where's the formula for VC? The formula for VC is right here. Okay, so it's just a matter of basically applying and putting these numbers in the formula. So here is the formula for VC. The digit that I have is 127, the same digit. 127. How much is R min? R min was 0. R was, in this case, 4096. V maximum is 10 volt, and V minimum in this case again is minus 10 volt, and V minimum again is minus 10 volt. Okay, so how much is the answer? The answer gonna be equal to, well, 127 by 4095, because 1 is off. Okay, this is the number that I have, and then 10 minus 10 is gonna be obviously 20. Why is it 20? Because that's the range that we have. 10 minus 10, and then 10 is taking that off. So here the number that I am getting is minus 9.3798, 97, yeah. Okay, so it's the number that I am having. So you can see that it is actually pretty different with what we had in the previous case. Pretty different with that. Why is that happening? Obviously because we're now talking about a different different A to D. The A to D is not the same one. The A to D in the previous case was 8 bits, but now the A to D in this case is 12 bits. So obviously they're not the same, and they are doing in a different, they behave in a different way. Okay, so this is example 7. Let's go for another example. Example 8. Okay, 12 bits. I turn it to 16 bits. A to D. The input range is from, I change the input range as well. From, okay. Now, it doesn't always have to be the voltage. It can be even the temperature, the input range, because the sensor has this input range, and then the input range goes to the voltage and then goes to the temperature. So this time, let's say that the input range is, for example, from -10 -10 -10 degree, okay, to, so it's sort of completely odd numbers, -10 degrees of Celsius to, I go for example, 120 degrees of Celsius. Okay, so we have a sensor. Okay, you have a 16 bits A to D connected to a sensor with the input range of, so you can see a little bit the wording is different, but well, the same concept. Okay, now determine the input value when the microcontroller PLC is showing. Okay, now I wanted to go for a different value, showing thousands. Okay, when the microcontroller or PLC is showing 1000, so actually a lot of things has changed here. This is more advanced question, obviously, because we have a 16 bits. Okay, so the information that we have 16 bits. That's one information, and we have a temperature range, which is different, 120 degrees. Okay, and we have a number that is 1000. Okay, what we should do here, well, let me solve it. Well, a lot of that is going to be similar, so actually we kind of need the similar sort of formula, but obviously number of bits going to be different. So copy and paste here. This time n is 16 because it's 16 bits. So let me change this value too. So guys, 2 power 16 equals 65536. Again, likewise, we consider r mean equals 0. We could have a different value, but well, in this case, in most of the cases that we have considered that. Okay, now VC equals D. Let me actually keep this formula and copy and paste it so you can see that how the value are changing. Okay, so now VC equals D, and how much is D? D is 1000. 1000 minus R mean. Again, we said the value for R mean equals 0. Well, actually, I don't say VC, now I say TC. Okay, and if it is TC, because it's temperature, is not voltage, but also instead of V maximum I have T maximum, and instead of V minimum I have T minimum, and instead of V min I have again, well, T min. So everything basically turned to time, not turned to the temperature. So Tc equals 1000 minus 1. Well, R that we have is how much? Is 65536. Okay, and then T max, as you can see, maximum temperature is 120 degrees. Okay, and the minimum temperature we said is minus 10, and again V mean equals again minus 10. Okay, so let's see how this A to D is going to work. 1000 divided by 65535. Why is it? Because obviously the number that we have is minus 1, so then here 120 minus 10 is gonna be 130 times that, and then whatever we're getting is minus 10. The number that I am getting is minus 8.0163, minus 8.0163. Okay, basically, I mean, obviously, yeah, 632715343, so sort of a more up continue on that, but well, we just leave it there for obviously the digits carry on and continues. Okay, on the same question, this time I wanted to look at, okay, have another example, okay, but this time talk about the error. Okay, well, let's actually go for that, the same question. So quit this question, section B of that. Let's say that how much is the error? Okay, or we can say that actually the digitization error, because this error, you may have other errors, but this error is caused because of the digitization. So it's basically because we are making this digitized. Okay, so what is the formula that we have? Let me turn this to blue. Here was the answer, here's the question, so we separate them. What is the formula that we had for the error? The formula that we had for error was, well, the error was here, V minimum, V maximum over 2R, as you can see. Okay, so again I write the formula, but then I know that I am not talking about voltage anymore, I'm talking about the temperature. Doesn't matter, so it's going to be T error, and instead of V I have T. T max minus T min over 2R. So it's pretty much the same, but well, it's different in that sense. Okay, So again, copy and paste in the formula to write the value in it, so hopefully it makes more sense. T error equals T maximum. Well, T maximum we said is 120 minus T minimum, that was minus 10, and 2R, and then R we said R equals this number over 2 times this number to see how much is the error. So 100 minus 10 is going to be 130 divided by, well, 2 times 65536. Oh dear, which is going to be quite a small number. Let me copy and paste it. And well, this value that we have, okay, let me just cut that till here. This value that we have, obviously we know that this value is not voltage. I was trying to convert that to formula. Centigrade. So the error is pretty low. That doesn't mean that actually the data that we have comes with this accuracy, because what's happening, you know that we have other errors, like for example the noise or other type of errors as you may think of. So well, we have multiple errors, we have multiple situations, as you know. Okay, let's go for another example, and hopefully you'll be able to answer that example. I like to go for multiple examples always. Okay, example 9. Let's say that you have an, well, actually it was supposed to be A. You have a, okay, I go for 8-bit. Again, sort of reducing it. Okay, 8 bits A to D connected to a sensor with the input range. Okay, before that it was a temperature sensor. Now I wanted to go for the level sensor. Level sensor with the input range of, okay, so change this number to for example 0 to 521 meters. So just some made up number. It's basically our sensor accuracy, our sensor range. So each sensor that you have is getting a different range. Okay, now the output of the microcontroller, I just wanted to change this to 100. Okay, now what's happening, we have meters. Okay, so it's not the value that we have, and then also we have calculate the calculate the error. Okay, so basically that is what we're doing here. Put that on the next line. Okay, so that you can see the whole page. Well, it's 8 bits, so the first things that we can work out is about the resolution again. So R equals 2 power 8, which is 256. Okay, but then again, the formula that we had here for TC, it turns to the level. So instead of TC, okay, I call that XC. Instead of Tmax, I go for, well, in physics usually we use X for that, for the lengths. If you like, you can use L, you can use D, doesn't really matter as long as you know what you are doing. Okay, now this is also the answer, so let's turn it to blue. So now it's just a matter of putting numbers in the formula and see what's happening. So I go and copy and paste this again. Oops. D minus R min, and R min here again is 0. R minus 1 and R equals, well, 256 minus 1. Okay, and here we have X maximum, and X maximum, as you can see, is 251. And X minimum, as we have it here, is going to be 0. Well, X minimum again is 0 for this case. Okay, how much is D? D was 100. So it is 100 divided by 255, and that goes to multiply the 251, okay, plus 0, which is giving us 98.43 meters. 98.4 meters. Obviously, it is not a very good accuracy. Why is it not a very good accuracy? We will see that because number of bits is just 8 bits. It's obviously not a very good converter. Let's have a look. So here this formula was for T error. And now I am not having T, I am having X error. So X error equals, what is the value that I have? Well, we said the range that we have is 251 to 0. So 251 minus 0. Okay, and here 2 times the resolution, and here the resolution is only 256. Okay, so let's see that how many meters it is. So 251 divided by 2 times 256. There's the resolution that I have is 0.49 meters. Okay, 0.49 meters means pretty much half a meter up and down. It goes half a meter up and down. So actually, if I get 0.49 meters as the error, so this 0.4 is pretty much at the range of the error. What does that mean? That means that, well, I know that my calculation comes with a lot of error. So that 0.4, what is that 0.4 is doing? That 0.4 is just sort of something nonsense. So basically it's better to just say that 98 meters instead, rather than just saying something that basically doesn't exist. Well, this is the X error that we have. Now, let's go for another question and other questions that we actually can demonstrate the frequency to give us more feeling of that. Okay, example 10. This time you have well, it was actually supposed to be an 8 bits. Here you have I go for 10 bits A to D connected to, okay, now I wanted to say that it's actually getting the voltage A to D to convert a signal with multiple frequencies. The highest frequency that may present in the signal is, for example, 1 kilohertz. Okay, we know that hertz is a scientist, okay, and we measure frequency on kilohertz because of that H, that you use H, capital H here. Okay. Now we have this 1 kilohertz here. So questions that we have here. 1, or let's say A, calculate the error. B, okay, determine the minimum sampling rate for the A to D to provide correct results. Okay, so basically we have these questions, okay, that we wanted to work them out. First of all, we wanted to work out that how much is the error. Okay, the error that we have comes from this 10-bit error that is available to us. So, well, we use the formula for error. This time the input is voltage, Okay, so what's happening? Instead of X error that I mentioned last time, well, it is going to be V error. Okay, now do I have the information that I require? No, I don't, because the signal range is not given to me. So let's have the signal range too. Okay, the signal fluctuates between -5 to 10 volt. Okay, I didn't want it to make it, usually it is symmetrical, usually it is like -5 to 5 or but I just wanted to give it a different range. So -5 to 10 volt. So if it is -5 to 10 volt, okay, and it is 10 bits, okay, the first thing that we need to do is actually not calculating this. The first thing is calculating the resolution. So R equals 2 power, well, we say 10 bits, 10 equals, well, 1024. Okay, now I have R, I should be able to work out the V error. Okay, so first of all, here 2 times R, so it's 2 times 1024, and then here I have 251 minus 1. Okay, 251 minus 1, so it's actually changing because my range now is -5 to 10 volt. So the maximum is gonna be 10, the minimum is gonna be, well, -5. So see that, how much is it? So 10 minus -5 is making, well, 15 volt, and over there it is 2 times 1024. Well, the error is pretty low. That's good. The error is gonna be 0.0073 volt. Okay, so it's like 7 millivolt that we have. Well, for some application you may need better error rate, but for many of them actually it is fine and you should be able to use it with no problem. Okay, so we have these things that we have here. So now the next question that we have, and it's actually an interesting question, is that how much would be the frequency? Well, frequency, the higher the frequency is actually better, but what's happening, there is a minimum frequency that could be acceptable, and less than that is not gonna be acceptable. So voila, the maximum frequency that we have, okay, so we say that the minimum sampling, okay, let me also change this to 22. The minimum sampling rate must be twice the highest frequency. So the highest frequency is how much? Okay, the highest frequency we said is 1 kilohertz. So the sampling frequency should be more than 2 kilohertz. We didn't say that how much, but it should be more than that. Okay, so how much? Well, more than that. Do you have any sort of range to sort of give that for this? Well, more than that is better. Well, I would say, because if you have a sine wave, especially if you wanted to do things like Fourier analysis, okay, well, I would say that at least we need something like 16 points, so which is much higher than that, to have a good understanding of the signal and sort of avoid getting unwanted noises and things like that. So I would go much above the signal that was actually given here, as we have that. Okay, that's this one. Now, what else? Let's have one other example. Okay, you have so this goes from 10 to 12, 12-bit A to D connected to convert to, so basically to convert, doesn't need connected, to convert a signal with multiple frequencies. Okay, the highest frequency may present, this time is for example 100 hertz. Okay, the signal fluctuation this time is changing from, okay, from for example minus 100 to 100 volt. I hope you should be able to do that and understand and try that. Well, calculate the error, okay, determine the minimum sampling rate for the A to D to provide that. Okay, that yeah, wouldn't be actually a sort of a big A to understand that and find that. Well, now adding one other things here, okay, the A to D, output is 10,000. Okay, determine the input. That's another question. I want you to actually answer this question. Okay, and the other one, the input signal is 59. Determine the A to D output. This is basically few things I wanted you to answer them. And guys, oh dear, I forgot to have a break here. That's okay. Okay, let's have a break. Let's then we actually can have and combine breaks. So come back at 15. Come back at 15:55. Okay, let's have a break, and then after the break we can anyway convert that and do the calculation accurate. So it's like a break time for us. Okay, that's a break time. Come back 15:55, and that's where actually we're going to practice this stuff, and we're going to look at this more and do the calculation accordingly. Okay, well, if you got any question, don't forget to write them down for me. I am looking at your notes now, and also if you got any sort of comment, just come in front and, well, we can talk about them and we can talk and discuss that. Hopefully you should be able to discuss, to look at that. So after the break, okay, after the break that we have, we're going to talk about the noise to signal to noise ratio, other errors, and we also talk about the first assignment that I would expect you to complete. Well, I hope it goes all well. So see you at 15:55 o'clock. Okay, thank you.